First of all, thank you for coming to this talk. And as Branko mentioned earlier during the keynote, Java and JVM is not only about the Java programming language. There are currently more than 50 programming languages implemented that run under the JVM, but all of them are implemented with certain level of difficulty. And the reason for that is because it's not trivial really to implement a programming language that runs in the JVM. It's performant enough. For example, if you want to run JavaScript or Ruby, you have to make sure that your language implementation is performant enough, that it gets good enough performance. And in this talk, we'll look into a new project that's been developed by Oracle Labs for the last couple of years. It's quite an interesting project. And just before we start, I would like to thank to Thomas Wurtinger, which is currently the project lead of GraalVM. The core team is based in Zurich, and they're really doing a lot of hard work in the recent few years to make the project more visible for the community. Just a few short words about me. My name is Martin. I'm running my own consultancy called Coffee Cup Consulting. I'm working on a few projects. I'm also one of the guys that runs the events of the Bulgarian Java user group. We are in total 5 people. We have our own community conference called JPrime. So if one of you is interested in giving a talk in Bulgaria, you can submit your presentation for JPrime. We cover accommodation and travel costs for accepted speakers. You can also follow me on Twitter at MartinFME. I typically talk mostly and 99% about Java. Just recently, I also authored a book on RabbitMQ. I'm quite fond of message brokers. So if any one of you has some questions or interest in RabbitMQ, you can find me after the session and we can discuss topics about RabbitMQ. So during this talk, first we'll discuss what is GraalVM and why is it important for you as a Java developer. Then we'll see how you can build your own version of GraalVM and how you can run it and manage it. Then we'll see some performance benchmarks on how basically the GraalVM positions in the existing JVM ecosystem. And at the end, we'll see some short directions and future directions for the development of the project. So GraalVM, what is GraalVM? Has any one of you heard about GraalVM? Just one person? Okay, that's good. So the GraalVM project is not a new one. It's been around for the last 4 or 5 years. It's a development effort by Oracle Labs to provide a new just-in-time compiler for the JVM. But before we dive into the GraalVM, let's provide some background information. Do you know what's the difference between static and dynamic compilation? No one? Really? Okay, so to give you some background information, static compilation essentially is the process where you statically compile your source code to some intermediate representation or to some machine code. For example, the JVM statically compiles Java source files to bytecode, and it also dynamically compiles bytecode to machine code. For example, if the JVM determines that it has some method that it needs to optimize, it runs the so-called JIT compiler in the JVM runtime that compiles your method and executes it directly in the particular operating system. As you can imagine, that's not really an easy process because typically the JVM needs to know how to generate machine code for a specific operating system and a specific processor architecture. So as you can think of it, it could be quite difficult and challenging to implement a just-in-time compiler that runs in the Java virtual machine. So this is how currently the JVM works. It statically compiles bytecode, so Java source code to bytecode, and at runtime it may dynamically compile bytecode to machine code. And in that regard, Graal is essentially a new just-in-time or dynamic compiler for the JVM. And the idea behind the Graal project is to provide the ability for both language implementers and you as Java developers to implement your own programming language for the JVM that makes use of all of the performance optimizations that have been over the years for the Java programming language. So the idea is basically that you write a parser for your own language, and when you parse your language and provide it in a separate data structure that runs in the Graal JIT compiler, you get the performance of the Java programming language without you as a developer taking care of what optimizations you need to do on your own programming language. And the cool thing about the Graal JIT compiler is that it's written in Java. So essentially, Graal works on a data structure that's represented in Java. And basically, it provides an API called Truffle that you as Java developers can use to implement your programming language. So basically, if you want to implement a programming language in Graal, you need to be a Java developer. In fact, the Graal JIT compiler generates machine code from a different representation of the source code. The standard Java JIT compilers generate machine code from bytecode, and Graal generates machine code from an intermediate representation called abstract syntax tree. An abstract syntax tree is a standard way to represent a programming language, and this is the approach that has been taken by the Graal team, to use that intermediate representation in order to provide different types of optimizations that allow you to execute your programming language much faster. Apart from that, GraalVM also provides a standard bytecode interpreter as the standard JVM that allows you to execute bytecode directly instead of providing it in that intermediate representation, which is an AST. In fact, the Truffle API is a Java API, as you can imagine, and it provides another intermediate representation. So basically, you write your own language in the Truffle API, and during compile time, it gets converted to this intermediate representation. And from there on, the GraalVM takes the responsibility to provide different types of optimizations on that AST. However, this AST that's generated by the Truffle API is not the same as the Graal AST. It gets converted to a second intermediate representation that is more convenient for different types of optimizations that are done by the Graal JIT compiler. The Truffle API uses Java annotations. We'll look a bit more into details of how a Truffle representation looks like. And an AST generated by Truffle is not only a control flow graph that represents the control structure of your programming language, but it's also a data flow graph that reasons about the different types of data that flow through that graph. For example, you can have a method that accepts an integer. This is one type of node in the graph, and you can have a method which accepts string, the same method that accepts string. So these are two different types of nodes, and the AST is basically aware of the data that flows through that AST. Essential feature of the Truffle API is also the ability to specify node specializations, as I just mentioned. So for example, you can have one operation that accepts string and another operation that accepts integer, and both are implemented in a different way in the programming language. And these are called node specializations. Here is it, how basically a Truffle interpreter is executed. So you write your own programming language using the Truffle API, and it gets compiled standardly by the JavaC compiler. As we mentioned, the Truffle API uses annotations to define the relationship between the different parts of your language structures. Those annotations get compiled by JavaC, and you get a generated interpreter source code, which basically provides the intermediate abstract syntax tree representation of your language. And that AST is executed by the Java virtual machine. And from there on, different types of optimizations are applied. Now, to get even more details about what is the architecture of the GraalVM, we'll track how is, for example, JavaScript executed in terms of Graal. But let's first look very briefly in the Graal architecture. On top of the layer, you have the different programming languages that are implemented. And below of them is Truffle, which is the Java API. You can think of Truffle as simply a Java library that you can use. Truffle API runs on top of Graal, which is the just-in-time compiler that runs your programming language and provides different types of just-in-time optimizations. And Graal can run on a standard JVM. However, at present, the Graal JIT compiler cannot run directly on the hotspot Java virtual machine because there is no standard interface for compilers as of Java 8 that can provide functionality of hotspot to just-in-time compilers like Graal. And there is a new Java enhancement proposal that is part of JDK 9, which is called JVM compiler interface, which basically provides a standard interface for just-in-time compilers like Graal to make use of the APIs provided by Hotspot, for example, to execute machine code more easily. And at present, for that reason, Graal provides two versions. One is a version that runs on a patched version of the JVM that doesn't use the Java compiler interface. And the other version can run directly on JDK 9 without any customizations. And that version basically makes use of this JVM compiler interface. GraalVM can also run on different other types of JVMs, like, for example, the Maxine JVM. The Maxine JVM is a research project by Oracle Labs, which is basically a meta-circular VM. This means that this is a virtual machine that runs in Java. The runtime of that virtual machine is not written in C++, but is written in Java. So that's in general the architecture of GraalVM. Now, to make even more clear understanding of how this works, let's see how a JavaScript interpreter works in Graal, for example. So let's say we have some JavaScript file, application.js, could be a Node.js file or another JavaScript file. For that reason, we create an interpreter for that JavaScript file. And basically, that interpreter contains a parser that parses the application.js file. By default, the Truffle API doesn't provide you with a standard mechanism to parse a source code file. You have to write the parser yourself so that you split the source code into different tokens. So when you write the JavaScript interpreter, it parses the JavaScript file that you pass to it and converts it to an intermediate representation, which is an abstract syntax tree that's represented in bytecode. When that abstract syntax tree representation of your source code is provided by the Truffle API at compile time, it is further converted to a more convenient form, which is a graph intermediate representation, which is another form of an abstract syntax tree. And when that happens, essentially, the GraalVM takes the responsibility to provide different types of optimizations on that Graal intermediate representation. As we mentioned, the GraalVM has both bytecode and AST interpreters, and the GraalVM in that case uses a special AST interpreter that allows you to optimize certain parts of that abstract syntax tree. For example, you have a method in that abstract syntax tree, you have a node that represents a method, and the Graal JIT compiler decides to compile to machine code that particular node and all of its sub-hierarchy. And when it compiles that node to machine code, it uses either the Graal hotspot adapter to execute that machine code. This is in case we have a custom version of the hotspot JVM, or it uses the JVM compiler interface to execute that machine code directly on in the JVM runtime. So when parts of the file are compiled to machine code, as we already mentioned, the machine code is transferred to hotspot for execution. However, at certain points, the JVM may decide that it's not really optimal to execute machine code, and it de-optimizes that machine code back to the abstract syntax tree representation of Graal. For example, when you have an exception, for example, if you throw an exception in JavaScript, the runtime may decide that it cannot handle properly that exception in terms of machine code, and it transfers back that exception handling functionality to the Graal JIT compiler. And that exception is handled directly by the AST interpreter rather than in the machine code that's being generated. So when basically this happens, there are special routines provided by the Truffle API that allows you at certain points to de-optimize source code that's been optimized by the Graal JIT compiler. So there are different optimizations that are being done by the Graal intermediate representation, and they are quite similar to what currently the JVM does with its JIT compilers. Currently, the JVM, as you probably know, provides two standard types of compilers. This is the client and the server JIT compiler. The client JIT compiler is optimized for fast startup times, but less optimizations at runtime. And the server JIT compiler provides slower startup times and more optimizations at startup, and less optimizations when your application runs. And Graal positions somewhere in between the two types of JIT compilers in terms of performance. So these are optimizations that currently exist also on the client and the server JIT compiler, such as method inlining. Do you know what is method inlining? This is, for example, when you execute a particular method in your Java application, the JVM decides that it should take the source code of that method and put it directly at the execution point rather than call a function. And this basically saves time in determining where is the location of that function that needs to be called. There are also other optimizations. We'll not discuss them in detail. We can go into more details after the session, such as partial escape analysis, inline caching, constant folding, and so on and so forth. And currently, there are several supported languages that are being currently finished, I would say. There is a JavaScript interpreter, which is not open source as of the time of this talk. Oracle has the idea to open source it in the next few months. We have R implementation. We also have Ruby implementation, which is called Ruby Truffle. And we have also some experimental interpreters for C, Python, Smalltalk, LLVM, and others. Now, the Graal team basically promotes the idea that every programming language written in the, that runs in the JVM should have an implementation in Graal using the Truffle API. So that basically the language goes and tries to see whether the Truffle API provides more optimizations than would a standard implementation that compiles directly to bytecode. And in order for you to get started with GraalVM and to understand how to write your own programming language, you can start with the simple language project, which has a syntax very similar to JavaScript. And the idea behind this project is to showcase how you can write your own programming language using the Truffle API that runs in a GraalVM. Now, the simple language project, I would say, is the best place to start if you're interested in writing your own programming language. There is still not enough documentation about GraalVM. If you want to see how something is implemented, you can get the source code. Basically, the GraalVM is an open source project. It's published on GitHub. And also, other language implementations are open source, as we mentioned. For example, Faster and Truffle and Ruby Truffle are open source. You can download them and see how they are implemented as well. And you can use that as a starting point for your own language. We'll see how simple language is executed in just a few seconds during the demo. Now, if you want to build your own version of GraalVM, currently Oracle provides binaries from the Oracle web of versions of Graal that run on a version of the JVM that has an implementation of the JVM compiler interface. That interface, as we mentioned, would be part of JDK 9, but currently there is a version which runs on JDK 8. So it basically is an extension of JDK 8. What really the Graal team hopes is that GraalVM would be part of JDK as of probably Java 10, but we'll see. There is a lot of internal struggle between the teams at Oracle that want to put that in place in the standard binary installations of the JDK. Yeah, this is what we already mentioned. GraalVM interoperates with the Java compiler interface, and it also provides its own custom version of JVM on top of which it runs. Early access builds are available for download for Linux, Windows, Mac, Solaris, for the supported versions operating systems. And if you want actually to build your own version of GraalVM, there is a very convenient tool provided by the Graal team, which is called MX. And that tool is part of the Graal project in GitHub. You can clone it, and if you want to build your own version of Graal, you can say mx --VM Graal build. And to run that VM, you can say mxvm. So as you can see, it's pretty simple. The only thing that you need in order to be able to build a version of Graal at that point is to have a JDK, a bootstrap JDK, that has the Java compiler interface provided. The MX tool provides not only a means for you to build your own version of JVM, but it also provides a lot of convenient utilities that, for example, allow you to update source code of Graal and to run JUnit tests and also performance benchmarks that are provided by the team. It also allows you to build separately not only the Java code of Graal, but also C++ source code that's provided for the custom implementation of the GraalVM. It also allows you to run different types of tools that are provided by the JVM. And these are, for example, the IGV tool, which is Ideal Graph Visualizer. This tool allows you to visualize this intermediate representation of Graal, which is an abstract syntax tree. And in that way, you can see how is your programming language represented internally. We'll demonstrate that tool shortly. And it also can be used to generate ID project files for you to get started developing with GraalVM under Eclipse, IntelliJ, or NetBeans. Now, let's see shortly how the GraalVM works. For that reason, I've cloned the GraalVM project in a virtual machine, because it's more convenient to build it in Linux. Under Windows, it's quite hard to build Java in general, and Graal, as you can imagine. So, what I've done first, I've downloaded a version of Graal. Can you see my screen actually? Well, okay. And if I want to execute a JavaScript file, let's say, with the version of Graal that I've downloaded, I can see a very simple JavaScript file that I have. It's called sample.js. And that file is pretty simple JavaScript that basically is nothing more than a function that basically iterates from 1 to some value and sums the values from 1 to that value and finally prints the result. And I execute that function with a value of 7. Now, if I want to execute that with GraalVM, GraalVM comes with tools that allow me to run different types of language interpreters. In particular, it provides me with a JavaScript interpreter that's not open source yet, but I can use it. So I would go to GraalVM bin, and I'll say JS. JS is the name of the tool that basically runs my source file in the JavaScript Graal interpreter. And I would say sample.js. As you can see, it's quite simple. It's as you would use other JavaScript language like Rhino from Mozilla or any other. And as you can see, I have the result printed. Now, this is okay. This is if I want to run JavaScript using the JavaScript interpreter. But what if I want to write my own programming language? Now, for that reason, we can see how is the simple language being implemented. I've cloned the simple language project, which, by the way, is available in GitHub. Let me just show it briefly. So in GitHub, essentially, I have all the projects, the Graal projects in one place. I think I don't have Wi-Fi at the moment, but all of the projects in GitHub are part of the GraalVM project. You have the simple language interpreter, you have the Graal core VM, and other projects. Now, if I want to basically execute a simple language, I can go to the simple language project, and I'll see a very simple example of simple language, which is example loop.sl, which is simple language. As you can see, in terms of syntax, it's very similar to JavaScript. I have a function that iterates up to 1 million, sums up the values, and finally returns the sum. As part of the source code of my simple language, I've provided the ability to measure the time that is required for the execution of that method. For that reason, I've provided an implementation of the nanotime standard operator as part of my language implementation. Now, if I want to execute that, I can use a runner provided by the simple language project. And if I look at that runner, which is provided by the run file, I can see it's nothing more than running the Java simple language interpreter. This is purely like a JavaScript library, like a Java library, where I pass basically the source code of my simple language. Now, if I run that, as you can imagine, it will run essentially that program. It will take some time, first for the JVM to start up, to warm up. And as you can see, on the first iteration, it executes for 1.4 seconds roughly. And next iterations are close to 0 milliseconds. And the reason for this is because the GraalVM, after the first run, managed to optimize that method. And if we go back and see how is the method implemented, you can see it's a quite simple method that can be implemented as a constant and not as a while loop. And the GraalVM managed to optimize that. Now, so far so good, but if you would like to dig a bit deeper, we can see how is basically what is the intermediate representation of my simple language program. And for that reason, I need to use the ideal graph visualizer tool that can allow me to dig inside what's the intermediate representation of my source code. For that reason, I have to go to the Graal core project, and I'll use the MX tool to run the ideal graph visualizer. For that reason, I'll say mx -- java home. I need to specify the bootstrap JDK. And for that reason, I have the so-called lab SDK, which you can download from the GraalVM download page. This lab SDK provides the JVM compiler interface as part of Java 8, which is not part of Java 8. And when I specify that Java home, I can say IGV to run the tool, and I can run the IGV tool. I have to wait for a few seconds. The ideal graph visualizer is a tool developed also as part of Oracle Labs. And as you can see, it's quite easy to start it with the MX tool. I'll be waiting for a few seconds for the tool to start up. And after the tool starts up, I need to print the intermediate representation of my source code file. In order to do that, I have to run again my simple language file. If I go back to the simple language project, I can say run, and I have to specify a few parameters that allow me to dump the intermediate representation to the ideal graph visualizer. Okay, if I do this, I have to wait for a few seconds. The intermediate representation is dumped directly to the ideal graph visualizer. I have to wait for some time for the representation to be put in place into the tool. And if I open basically what's being created in the ideal graph visualizer, it's not really a fast tool. And you can see here what is the intermediate representation of the program that I've just executed. At the beginning, I have an SL root file, which is the starting point of my language. And then I have some function body, which is the main function of my method. If I go back and see my source file, here is the main function. And to that main function, I have an SL function body. Then I have an SL block, which represents the actual block of source code. And inside of it, I have nodes for all the root level elements. I have a node for assigning of the iteration variable. I have a node for assigning the value variable. I have a node for the while loop and a return value node. And these are here. So this is how basically your application looks in terms of the Graal AST that's being provided. And that was really what I wanted to show you. At the end of my slides, I have a few performance benchmarks that basically show you how the GraalVM positions according to other language implementations that are out there for the JVM. And typically, the GraalVM performance is quite good compared to standard compilers for most of the languages out there. So essentially, that's it. Thank you. If you have any questions, you can find me after the talk and we can discuss. Yeah, just one.
Question. Is it possible to use existing Java libraries in combination with this VM and with other languages? For example, is it possible to use Java libraries using JavaScript language?
Absolutely, absolutely. Since everything runs as bytecode, because this intermediate representation, this AST that we show in the ideal graph visualizer, if I haven't closed the tool, I've closed it unfortunately. No. This intermediate representation executes as bytecode in the JVM. This means that you can use any Java library that is out there. Welcome. Okay, thank you everyone once again.